Hello, this is Jack Jackson. In this video, we're going to be looking at using a Jacobian to change variables in double and triple integrals. So before we do that, as we usually do in Calculus 3, we're going to look back at a similar kind of problem from Calculus 1. Okay, so here I have the integral from 0 to square root of pi of x times sine of x squared dx. Now, that's not one of our basic things that we would do for memorize for an antiderivative. So we're going to transform this using a change of variables, which is also called an integration by substitution, or the reverse of the chain rule, the unchain rule, if you want to call it that. So we see that we have the sign of something that's a little more complicated than a single variable, so we let that be the u. So we let u equals x squared. Then du is just the derivative of the x squared, the du over dx times dx. So the derivative of x squared is 2x and dx. So du is 2x dx. Now, I can group this correctly this way. I get sine of x squared here. I want this whole thing to be 2x dx because that's going to become du. The x squared is going to become u here. Now, I almost have that. I've got the x here. I've got the dx. I can insert a 2 if I balance by inserting a 1/2, which I can bring out front. Then this part in parentheses here at the end becomes du. This x squared becomes u. And we have an integral with respect to u. But notice you also need to change the limits of the integration. Okay, so we notice that these are x values. Well, if x is u, x is 0, u is also 0 because 0 squared is 0. So x equals 0 implies u equals 0. So that's an x of 0. This is a u of 0, but they're the same point. Okay, and then the other one here, if x is the square root of pi, then we plug in here and square it, we get pi for u. So it changes here. So be sure that when you're doing this, of course, that you're changing x's to u's, you're also changing the limits. Now we can find an antiderivative, which was kind of the whole point. The whole point was to find something that we could find the antiderivative of. The antiderivative of sine u is the opposite of cosine of u. So I put the negative out front, and then I evaluate cosine u from u being 0 to u equals pi. So substituting in for u, I substitute in pi and 0 and subtract those things. Cosine of 0 is 1, cosine of pi is -1, -1 minus 1 is -2, times -1/2 is 1. And so that integral is just 1. Okay, so I'm going to do exactly the same problem, but I'm going to think of it in a slightly different way. And I'm going to do this because it generalizes nicely to what we want to do with the double integrals. Also, this next technique is sometimes used in Cal 1 and Cal 2 as well. So it's the same thing, but a slightly different way of looking at it. So it's the same integral. I'm going to integrate from 0 to square root of pi. So that means the domain for this integral is this, this blue interval from 0 to square root of pi. Here it is on a number line, the x number line. Okay, so you have an x-axis or x number line there. And I want to transform the interval to a new interval from 0 to pi, but this time the variable is u down here. So again, we make exactly the same substitution, u equals x squared, but this time I want to notice that on this interval from 0 to pi, 0 to square root of pi, that this function that we're integrating is actually a one-to-one function. So it has an inverse function as well. So I can solve this for x. Actually, not the one we're integrating, excuse me, is not the problem. It's the one that, it's this function that's one-to-one for u equals x squared. Now, normally that's not a one-to-one function if you let the domain for x be big enough. But if we restrict x's between 0 and square root of pi, this is one-to-one, so we can solve for x. X is the positive square root of u, or in other words, u to the 1/2 power. Now I want to find dx, which is dx over du times du. So the derivative there is 1/2 u to the -1/2 du. Okay, so this is the same thing with a slightly different version of the substitution. So now what I do is I just go through and take each piece. I take the x and replace it by u to the 1/2, which is right here. I take the x squared, which is u, and replace that here. I take dx and replace it by 1/2 u to the negative 1/2 du here. Notice that there is a factor here besides just the du. That factor is dx over du. Now I also change the limits from 0 to square root of pi for x's to 0 to pi for u's, and that's transforming this interval into this one. So you can imagine this interval kind of stretching into this one down here. And so there's this transformation that maps this interval on the u's into that interval onto that interval on the blues, and it's 1-to-1. So there's an inverse transformation and it maps back the other direction. And what does it do with the endpoints? Well, it sends 0 to 0 and square root of pi to pi, just like we saw on the previous page. And so those are our new intervals. And then with the substitution, well, look what happens. We do a little algebra here. The 1/2 can be brought out front. The u to the 1/2 times the u to the negative 1/2 is just 1. That cancels. And so we get sine of u du. Now from there on, it's exactly like the previous page. So in this case, the domains are both intervals. So there's not really any advantage from one to the other. One interval is about as good as another. But the integrand, the thing we're integrating, is a little bit easier. So this is basically what's happening with you have the chain rule or integration by substitution. I guess the unchained rule. It's how you change variables in 1D, one dimension. Now, thinking of it this way is going to generalize pretty nicely. So let's review what we have. In general, we have some function f of x that we're integrating from some constant x1 to some constant x2. Of course, those are x values because this is the variable dx, differential dx, variable x. And we switch things to u's. So x is replaced by some function of u. So ultimately, this f of x of u is just some formula with just u's in it. And then we change dx to du, but then we have this extra factor, dx over du. That's how the chain rule works. That's how substitution works. That's how u substitution works. And then we change our limits to new u limits, which are just the u's that go with this x and the u that corresponds to that x. Okay, so that's what we have here at the top. And I wanted to point out in particular that there is this extra derivative right here as part of the substitution. Okay, so this generalizes nicely to 2 dimensions. If we have a double integral, we start with some region in the xy plane, some domain, could be any kind of a shape there in the xy domain. We're integrating that, f of xy dA, same I can think of dA as dy times dx or dx times dy. And then we want to transform that into a new integral, which is a double integral in the UV region, UV plane. It's some kind of region there. So a new domain over there for the UVs. It's just like transforming this interval here, but now it's going to be in 2 dimensions, so we're transforming two two-dimensional shapes. You replace x and y by some function of u and v, and then plug that into the function f, and now you got this whole thing here is a function of u and v ultimately. And then you change dy and dx to du and dv in one order or the other. But then you have a derivative right here in red that goes in place, just like you had a derivative up here. But this derivative is a differential expression. This is called a Jacobian. It has to do with some partial derivatives here. Okay? Now, again, why would you do this? You might do this to make the region easier to describe, and thus easier to come up with these limits here for these integrals on the iterated integral. And, of course, you might do it so that when you get to the end here, you get a partial derivative, partial antiderivative easier to find of your integrand. Okay, so now over here, there was no really difference in the intervals. There was a different interval, but they're both just intervals. So there's not a lot of advantage on setting it up in terms of the limits here, but it's the integrand that needed to be easier. Over here, you still have that, but then you also have the fact that the region itself might be much easier to describe in the new system, and that's going to be at least as significant as the other part. So as a double integral, of course, this means, let's say if we think of dA as dy, then dx, we integrate with respect to y first. These y's are functions of x for our limits, as you know, and the x's here at the end are constants for the last one. Over here, the first or inside limits are the first one, which is right here, second integral sign, but it's actually the first one done, goes with the first variable here. So the inner integral, or first integral, is respect with u, the way I've got it set up. So these u's are functions of v. So this will be some formula with v's. This will be a formula with v. And of course, these v's at the end are just constants. So ultimately, there's not going to be any x's and y's in this, just u's and v's. So this little thing is called a Jacobian. It's a type of derivative, sort of. And here's what it is on the left. It's actually the absolute value of a Jacobian. So these bars on the outside are absolute value. Now, this type of expression, you have a product minus another product. That can be represented as the determinant of a matrix, which is probably the easiest way to work it out and remember it. So on this, the inner vertical lines are actually determinant. The outer vertical lines are an absolute value. Of course, what you do the determinant, you get a scalar, or in this case a scalar function of u and v, and then the absolute value on the outside. So this is exactly the same. Remember how the determinant works. You multiply across this diagonal and this diagonal and subtract. So it's the delta x, or partial derivative of x with respect to u times partial derivative of y with respect to v minus the product along this diagonal, partial derivative of x with respect to u times partial derivative of y with respect to u. Partial x with respect to v times partial y with respect to u, I should have said there. Okay, and so that's the last one. So anyway, this is exactly the same as what you see here. The last version is just sort of a condensed version of the way we write this sometimes. It doesn't really say what it is. It's just a notation. But you see it looks like partial of the order pair xy over partial order pair uv. That doesn't really make sense by itself, but we just take that to mean this first thing, or the middle one. All right, let's see if we can actually compute a Jacobian. If you'll write this down, I think that you can actually do this next one on your own. Press pause now and see if you can work this out yourself. Of course, to be able to do this, we need to have x and y as functions of u and v, which I have given to you here. So it's pretty straightforward to do this, since you know how to do partial derivatives at this point, hopefully. So there's the sort of Jacobian notation. And then I'm going to rewrite that as a matrix with a determinant here. So the determinant of a matrix. And so the upper left corner is the partial of x with respect to u. So that's the partial with respect to u, partial derivative that is, of 4u squared plus v cubed. Moving to the right, upper right corner, partial derivative with respect to v of the x. So that's, again, of the 4u squared plus v cubed. And the bottom, we just switch out the function for the y function. Partial derivative with respect to u of the y, 3u plus 2v goes there. And the lower right is the partial derivative with respect to v of the y, which is 3u plus 2v. Now, let's actually do those derivatives. The partial derivative with respect to u, remember we treat u as a variable, v as a constant. So this becomes the power rule, that's 8u, and then plus 0. So that's just 8u. Upper right, partial derivative with respect to v, the 4u squared is a constant, or treated that way anyway, in the partial derivative. That goes to 0, and then the v cubed is 3v squared for the derivative, partial derivative. Down at the bottom left, the partial derivative there is 3, 0, and then the right bottom right, derivative of the first part's 0 and the last part's 2. So here you've got 8u, 3v squared, 3, 2, and we do that determinant, so it's 8u times 2 is 16u minus the 3 times the 3v squared is 9v squared there. So the absolute value of that determinant is the absolute value of 16u minus 9v squared. That's the absolute value of the Jacobian. So pretty straightforward to compute. Now let's look at a situation where we might want to actually use this. All right, there are several things on this page here. Let's start with this parallelogram. So we have some function we want to integrate. We'll get to that later. But this is the domain that we want to integrate over, is the inside of this parallelogram ABCD. A is at 6, 2, B is at 9, 3, C is at 10, 5, and D is at 7, 4. And so you go from A to B to C to D back to A, makes a parallelogram, and you want the inside of that. Now this is in the XY plane. So this coordinate system at this point for the parallelogram, the horizontal axis is X, and the vertical axis is Y, just like normal. Now if we wanted to integrate over this and set up an integral, regardless of what we're integrating, we have a little bit of a problem. It's not insurmountable here, but it is a little bit of a hassle, because if you start with a vertical strip here, you do not have a consistent bottom and top to the strip. Same way if you use a horizontal strip, you do not have a consistent left and right. So for example, if you look at a vertical strip, you start over here between 6 and 7. The bottom of this is given by the formula for the red curve, the AB, line segment AB, and the top is this line segment AD. But if you're between, say, 7 and 9, the bottom is the AB, the red, and the top is CD. Up here, the blue one. And if you go from 9 to 10, the bottom switches again to be this purple side here, BC, and the top is the blue side, CD. So at best, you're going to have to split this into 3 different integrals and set them up and do the integral that way. It's certainly doable, but that's maybe a little bit of a pain. It'd be a lot easier to do if this was, say, the easiest thing possible would be a rectangle like we have over here. So what we're going to do is we're going to transform this parallelogram here into this rectangle over here on the left. Now this rectangle is not in the XY plane, it's in the UV plane. I've got them sort of drawn on the same coordinate system here, but I want to think of this as in a new coordinate system where the horizontal axis is U and the vertical axis is V. And I want to do this in such a way that I take this point A and map it to A prime, which is at the origin in the UV system. So the point 6, 2 in the XY is going to go to the point 0, 0 in the UV system. Furthermore, I want this red side, AB, to be mapped to something going along the horizontal axis. Now remember, the horizontal axis is the U-axis down here, so it's going to have a coordinate or equation V equals 0. So I want this red part to be mapped to V equals 0. Similarly, I want the green part to be mapped to this vertical line here at U equals 0, which is on the V-axis. Okay, so to see what to do for the substitution, I need to come up with equations for the sides of the original parallelogram back in the old XY plane. Well, luckily these are just lines or line segments, so we know how to find equations of line segments. That's not too hard. I'll use the point slope form here to start with. So we're starting with the bottom, which is A to B. That is from 6, 2 to 9, 3. If we have 2 points, we can find the slope. If you notice, we're going to the right 3 and up 1, so that's a slope of 1/3. And then it's parentheses x minus the x coordinate of A, which is 6, plus then outside of that, the y coordinate of A, which is 2. So it's 1/3 parentheses x minus 6, close parentheses, plus 2 equals y. And now, I want to solve this for 0. Why do I want to do that? Well, I want to map this thing down to V equals 0 So if I can get this equal to 0, v is just going to be the other side of this. So I multiply both sides by 3 here. I get 3y equals x minus 6 plus 6. 6 plus a negative 6 is 0. So basically I have 3y equals x. So subtract, I get 3y minus x equals 0. Now at this point I actually have two options. I can either let v be 3y minus x, and then v will be 0. Or I could let v be the opposite, x minus 3y. And I'm going to show you, I want this to have positive coordinates, so it turns out that I want v to be 3y minus x, and I'll show you how I can see that by looking at the top of our parallelogram. Top of our parallelogram is just a line segment going through the point 7, 4, and 10, 5. Again, the slope is 1/3. You go to the right 3 up 1. That's slope of 1/3 is parallel to the base, so it is same slope. So y is 1/3 parentheses x minus the 7 plus 4, because 7, 4 are the coordinates of D. Okay. Multiply both sides by 3. You get 3y equals x minus 7 plus 12. 12 minus 7 is 5. Once again, if I get the 3y minus x, if that is v, then the top then becomes v equals 5. If I use the opposite here, the top would be down at negative 5, and this thing would be flipped down in the fourth quadrant. I'd prefer it up here, so I'm going to use v equals 3y minus x, and it works out. Now we could double check some of these things if you want. It's probably a good idea to do that. Notice down here, whichever one of these I put in 6, 2, it works out. So let's go ahead and just check the bottom one, since I've done a little algebra there. 6 for x, 2 for y. 3 times 2 minus 6 is 0, so that works. Let's check this other point here, 9, 3. 3 times 3 is 9 minus 9 is 0, so that looks correct. Let's check this one up here, 7, 4. 3 times 4 is 12 minus 7 is 5, that's good. And let's check out 10, 5. 3 times 5 is 15 minus 10 is 5, so that checks out. So it looks like I've done my algebra correctly so far. Okay, let's look at the left side here. We want to map it to u equals 0. So again, I want to solve it for u, but first I need to find at least some version of the formula. Well, this is a line segment going from 6, 2 to 7, 4. It has a slope of right 1 up 2. That's a slope of 2. So y equals 2, parentheses x minus 6 plus 2, using a as our sort of our center point. Distributing the 2, you get y equals 2x minus 12 plus 2 is minus 10. And then I want to get 0, so I actually want to do 2x minus y minus 10 equals 0. I could either do, again, I could do that or its opposite. We'll see which, it turns out this is the best one to let be u. Okay, let's just double check that we did that formula right. Plug in 6 and 2, it should work. 2 times 6 is 12, minus 2 minus 10 is 0. And then 7, 4, 2 times 7 is 14, minus 4 is 10, minus 10 is 0. So that works as well. So that's the correct formula. And so I'm going to let u be 2x minus y minus 10. And then this side will map to u equals 0, which is up here. Okay. Now let's go ahead and do the right side here and make sure we want to do the 2x minus y minus 10 and not its opposite here. This is a line segment going from 9, 3 to 10, 5. Again, that has a slope of 2. So y equals 2 times x minus 9 plus 3. Distribute, that's 2x minus 18. 18 plus 3 is negative 18. Plus 3 is negative 15. Okay, but I want it to be 2x minus y minus 10 equals some constant. So notice you have 2x minus y minus 10 and then equals 5. Okay, which would be a 0 here would be minus 15, which is what we had. Okay, let's just double check that last version to make sure it works. So we got 9, 3. 2 times 9 is 18. Minus 3 is 15. Minus 10 is 5. So that works. And then 10, 5. 2 times 10 is 20. Minus 5 is 15. Minus 10 is 5. Okay, so that's correct. And you can see now it is the equation of this side is just u equals 5. Okay, so that's going to give you a vertical. This is going to give you a nice little, well, a rectangle. Well, actually, even a square, actually. So now if we transform the formulas for each side, the bottom becomes v equals 0. It's across the bottom. The top side becomes v equals 5. The bottom side, left side becomes u equals 0. And the right side is u equals 5. So the sides are constant functions, which are horizontal and vertical line segments. And just double check the endpoints here to make sure how far out we go everywhere. A prime, the image of A, would be to take these formulas and plug in A's coordinates, which are 6, 2. 2 times 6 minus 2 minus 10 is 0. And 3 times y, well, it's 3 times 6, and minus the x, which is 6, it is, y is 2, x is 6. 3 times 2 minus 6 is also 0, so that maps where we want it to. And similarly, you can see the details worked out there for each endpoint. So you see that the endpoints really are at the origin, which we sort of engineered that to be that, and it turns out that the other sides are at, the other corners are at 5, 0 for B prime, 5, 5 for C prime, and 0, 5 for D prime. And so that effectively transforms this parallelogram into this rectangle. So here I want to show you kind of what's happening in a visual sense. This is using Geogebra, which I built this in. So here's our original parallelogram, and it's going to be transformed into this, and you can visually see that transformation. And so there's the function going this way, and then the inverse function maps it back this way. And so you can see that being transformed. Of course, this is actually in the xy plane over here, and in the UV plane on the rectangle. And so we're mapping those pieces like that. Okay. So we want to find a Jacobian. We need to have not u and v in terms of x and y, but rather the other way around, x and y in terms of u and v. So I need to solve these things around. So a little algebra going on here. Let's take a look over here on the right side. Alright, so let's take the first equation and solve for y. I'm going to add y to both sides and subtract u. So y is 2x minus 10 minus u. And this is a simultaneous system, so I'm going to substitute that in place of y in the second equation. b equals 3 times that y minus x. And that y is, of course, 2x minus 10 minus u. So I have this expression right here. Distribute the 3, and I'm going to, let's see, this gives me 6x, minus that 1x is 5x, minus 30 minus 3u equals v. And I want to solve this for x now. So let's see, 5x is, let's see, I need to add 30 to both sides and 3u to both sides to get the 5x by itself. So 5x is 3u plus the v plus 30. Divide both sides by 5. X equals, I'm going to distribute that 1/5. 3/5 u plus 1/5 v plus 6. And divide all those things by 5. All right, so now we have x in terms of u and v. I go back here to this expression and put in for x what it is here. So at y is 2 times the x minus 10 minus u. In place of the x, I put this 3/5 u plus 1/5 v plus 6. and just clean this up a little bit. Distribute the 2 and combine some like terms. Let's see. Let's just distribute first. This is 6/5 u plus 2/5 v plus 12. Then you got your minus 10 minus u. 6/5 u minus 1 u. That's 6/5 minus 1/5 is 1/5 of u. And then I have 2/5 v, and 12 minus 10 is plus 2 here. So pulling those down here together, we now have x and y in terms of u and v. So we went from u and v in terms of x and y to x and y in terms of u and v. And just to double check that those are correct, I should be able to take my u and v coordinates here for a prime, b prime, c prime, and d prime, and they should go back to the appropriate coordinates for a, b, c, and d accordingly. And so here's what I did. I worked that out. The details are worked out here, and they all check out. So I'll let you look at those details on your own. Pause the screen if you need to look at them, but that's what that is, and it's just a double check to make sure everything is right. And there are a lot of little places you can make a little algebra mistake. It's good to kind of check things as you go. And anytime you have a nice way to check things, you know, that's good. Okay, so again, this figure is in the xy coordinate plane, the original parallelogram. We transform it over to this rectangle in the uv coordinate plane, and we do it by the transformation of variables, where we substitute u equals 2x minus y minus 10, and v is 3y minus x. That's equivalent to saying x equals 3/5 u plus 1/5 v minus 6, and y equals 1/5 u plus 2/5 v plus 2. Okay, so with this second version, where x and y are in terms of u and v, we can now find our Jacobian. So let's do that next. All right, here it is on the right here. Okay, so we need the derivative of the x with respect to u here. Derivative of x with respect to v here, derivative of y with respect to u here, derivative of y with respect to v here. Okay, well these are just linear functions in two variables, so it's pretty easy to find derivatives. This one's just going to be the coefficient of the u. This one's going to be the coefficient of v, so that's negative 1/5 and then 3/5. And this one's the coefficient of u, which is negative 2/5, and this one's the coefficient of v, which is 1/5. So this is a nice constant thing here. Remember, in general, this could have u's and v's in the formula here, but in our case, it turns out to be constant. So negative 1/5 times 1/5 is negative 1/25, minus a negative 2/5 times 3/5, that's plus 6/25. That's 5/25, or 1/5. The absolute value of that is 1/5. So the absolute value of the Jacobian is actually just 1/5. All right, now let's actually do an integral. Let's say we just use a double integral to find the area here and the area here. Okay, that's just to find the area of the original one using a double integral. So you're just integrating the function 1 over this domain here. So we're just taking dy dx over the original domain, which is our parallelogram, and that's going to be the area of the parallelogram. Well, a transformed domain in this is the rectangle here in the uv plane is going to be integrating with respect to u and v. Nothing to transform for the integrand up here, but we do have our Jacobian right here. And that Jacobian, the absolute value of that Jacobian was 1/5. So that 1/5 can be brought out front of that first integral. Integral of du, the antiderivative is just u. Evaluate from 0 to 5 is 5 minus 0, which is 5, times the 1/5 is 1. Then the antiderivative of dv is just v. Going from 0 to 5 is 5 minus 0, which is 5. So what that's saying is the area of that original parallelogram is just 5. But you also may notice that it's actually 1/5 of the area of the rectangle that we got. Which is kind of explains why that 1/5 has got to be there, because it's sort of a scaling factor of sorts. So this original area of 5 is 1/5 of this big area here, which is 25. Now these are real simple shapes, so we can actually check the areas using elementary geometry to make sure everything checks out. Now these lines are all slanted, so it's a little bit harder to figure out the height of this parallelogram to use just base times height, but there's another way to get to it that's pretty easy. We can draw a rectangular box around this thing where the sides are vertical and horizontal. And if you look at the area of the whole thing, if you look at it, this is 1, 2, 3 tall by 1, 2, 3, 4 wide. So the area of the whole rectangle here is 12. And then we take away the unshaded pieces, we'll be left with the area of the parallelogram. So how about, what are the unshaded pieces? Well, there's a square down here in this corner and this corner. Those are each 1. So there's 1 and 1 there. If you'll take this triangle right here and put it with this one, that makes a rectangle that's 3 wide and 1 tall. So there's another 3 we have to subtract. And this little triangle here on the left and the one on the right, put those together, and you've got a rectangle that's 2 tall and 1 wide. That's an area of 2. So we're going to have 12 minus 3 minus 2 minus 2 1s. That's 12 minus 7 is 5. And notice that is 1/5 of this, which is just 5 times 5. It's 25. 1/5 of that is 5. So at least it does work out in this particular case. So in this case, you can see that that Jacobian of 1/5 is what we needed to adjust, but for the fact that we sort of stretched and expanded this region as well as transforming it from a parallelogram to a rectangle. Okay. Now, another way that we want to look at this is, well, will this work always? Is this Jacobian always the right thing to put in there? And of course, the answer is yes. But why is that? Well, think of this original parallelogram and think of a vector S and T being these two sides of this coming from one of the vertices, let's say from A. Okay? The area of that parallelogram, which I'm going to call delta A for right now, is the norm of the cross product of these two vectors. Remember that from our work with vectors earlier. Okay? So what I want to do is figure out what these vectors are. Well, we want those vectors, though, in terms of u and v, not in terms of x and y. But here, basically, here you have this vector is basically just delta x, delta y. But what is delta x? Well, it's x of this one here, of the b first. Well, that's going to be there's some delta u as well, right? So that's just going to be u plus whatever delta u gets us there. And then the v, right? Because on that, minus the x of this uv. So again, we want this one to transform over here to horizontal, so that the v is going to be constant. So we want to think of the v as being a constant here, but the u is changing. So we got a u here, we got a u plus delta u here. So take x of that ordered pair minus this one. This is basically delta x. And what about delta y? Well, delta y here, again, we want to think of as v is not changing here, right? V is a constant where we're mapping this to. So so we have y of the uv is where we started, and then we have the y up here, which is y of, well, u plus delta u comma v. So that is delta y. And these need to be thought of as 3D vectors. Okay, so then the z, delta z is just 0. because these are vectors, 3D vectors, but they're in the xy plane. Well, if you look at that, this right here looks a lot like the denominator, or like the numerator of derivatives. This is just your partial derivative of x with respect to u, well, times some delta u. And this is your partial derivative of y with respect to u times some delta u. Well, at least approximately, that approximation is going to be true for some small values of delta u. Okay, and actually, since this actually is just a parallelogram, it's probably actually equal here. Okay, so this t is going here. Remember, it's going to be mapped to something that's vertical. So now we're going to think of over here the u is the constant. So a similar way we do delta x and delta y for this here to make our vector. So the x component's delta x, which is x of u v plus delta v minus x of u v. So again, this is our x here, which has uv coordinates over here, and this one has the x has got the same u, but the v is moved by delta v. And similarly for y here, again, z is 0. So this is approximately the partial derivative of x with respect to v, comma, partial derivative of y with respect to delta v, and 0. And then what we want to do is take the cross product of those two things and do the norm of that. Okay, so we do the cross product here. We set up our determinants, I, j, k vectors. Here's our s vector. Here's our t vector. Now, since these are both zeros for k, there are no the I and j components are 0 here. Okay, so the vector, the cross product, is going to be pointing straight up out of the plane towards the viewer here, perpendicular to the xy plane. So it's just going to have a positive k component. Okay, so now we work this out. This is for expanding by k, it's just the determinant of this part right here. Okay, and it's just the product here minus the product here. Okay, and if you notice, they both have a delta u, delta v, which you can bring out front. Now we start taking limits of all this stuff. You get delta a becomes the dA, delta u and delta v become du and dv, and this becomes actually accurate here for the differential. Now that makes sense for this being a parallelogram. Well, what if it's some other kind of a shape? Well, what we basically do is these sides could be curved, okay, but basically what we do is we approximate this by making it into smaller and smaller slices, and we basically approximate the sides with little secant vectors here, and then approximate the area of the little subpiece that we have, which has an area of delta A, to be the product of these vectors. And when you take the limits, everything works out correctly. Now, that's not a complete formal proof. See your book for a little bit more explanation of that, and then a more advanced book on advanced calculus or mill analysis that will maybe go over that formally in the proof. But I think this gives you hopefully enough idea to see that this is going to work out okay, and it's actually going to generalize fairly well for 3 dimensions as well. And so here we see the Jacobian for 2 dimensions as actually it's the absolute value of the Jacobian here in determinant form. And here we see the same thing for 3 dimensions, and of course it generalizes exactly like you would think it would. Across the top row of your determinant, you have the partial derivatives with respect to x of u, v, and w, your 3 variables. And down here you have the second row, all, again, u, v, and w are the variables with which you're taking the derivative. And then the tops are all y's, and similar for z in the last row. So this would be the factor that we would introduce when we're changing from, say, dx, dy, dz to du, dv, dw. You'd also have to put in this factor here when you're doing this in 3D. So hopefully that gives you a nice little introduction to change of variables and using Jacobians to do that for double and triple intervals.